Good morning, everybody. Wow, what a great meeting, and just prelude for what's coming next as we go forward. You have probably one of the best plenaries coming at you in just a few minutes from the team. They're going to talk about all the great stuff that's happened over the last 6 months as they put the facility together. And I mean facility from where photons hit stuff to get to California to go through processing and end up on a science platform for you. But look, an observatory is much more than just telescopes and long haul networks and data facilities. It's really about people. And there's many, many people that make up the observatory in the community. And I want to recognize some of those here this morning for their very, very important contributions these folks make every day, and without which the observatory also would not succeed, just like it wouldn't succeed if we don't get the image quality improved, right? So these folks on the right, I mean, they are, you don't have to pay attention to my name, but the folks on the right side here have done just an amazing job for the observatory, and in particular for this meeting. If you're in the audience and I read your name, stand up and wave to everybody. And if you're online, wave your hand or something. Emily Acosta, Rob McKercher, Thu Nguyen, Marina Pavlovich. David Rathfelter has done a tremendous job with our IT here at the meeting. It's just a fantastic hybrid meeting. Thank you, David. Nora Robledo, Regina Matter, and Glenniver Charles Emerson have manned the booth all week for you all and done a fantastic job. Christine Sodal from Slack, Kristen Metzger, Rand Powell couldn't be with us, but she has built the foundation with which a lot of these folks are running on now. Phil, as always, is helpful in every aspect of running the observatory. Heather Shaughnessy at Slack, thank you, Heather. And then, one person here got thrown into the deep end about a month ago or 3 weeks ago, and that's Carolina Borgia. And I just want to thank her specifically because the meeting has really come off quite well. Thank you, Carolina. Thanks to everybody. And we have a fantastic science organizing committee. This meeting has a lot of history. It's a great meeting. The history of this meeting starting off with deep project discussions and sessions, and then evolving slowly as we got closer and closer to science, and really on the precipice of a huge amount of science as we saw this week. So thank you very much to our science organizing committee, Shaira Anad, Mariano Dominguez. If you folks are in the audience, please wave at the folks. Melissa Graham, as always, does a tremendous job organizing this meeting and managing many aspects of it, including the science program. Laura Alex Maltz, Lucia Marchetti, Simona May, thank you very much. Gautam, of course, thank you. Bernadita Reed, Wachaya, Matthew Weisner, and Weijian Yu. Thank you so much for your contributions. And then our ex officio members, Federica, as always, is present, Igor as well. Rob Seaman, I haven't seen Rob this week. Is he here? No, maybe we'll see him tomorrow for his extended ADAS meeting. Andrew Sterner, and again, Thu Nguyen. Thank you very much, everybody.
Great, got that annotation to go away, the red line, I did it. Thank you, Tiago, or Timo helped with that, yeah. Oh yeah, wasn't good, sorry. Okay, usual reminders that we have a code of conduct. COVID-19 is still out there. The registration desk is a lost and found, and that people have social batteries. Reminder to stay muted if you're on Zoom. Try not to hit that annotation button, and yeah, use the microphones in the rooms today, please. We have our exit survey. It's up, it's ready for you. We do review this feedback and we make changes every year. We go through it, compare with last year's, and try to make this a better workshop for everyone. So please do go there and fill it out. It's going to come out in Slack. It's going to come out by email. So you will also have the link, and the survey will be open until Wednesday, August 13th. Save the date, Rubin Community Workshop 2026. It's going to be July 27th to 31st, and we'll be back at Slack in Menlo Park. That information is also coming out today by Slack and email and all that stuff. And just one final thing for all the community contributions that make the Rubin Community Workshop work, all of their session chairs, every speaker, every panelist, every poster presenter, everyone who comes in the room, asks questions, listens to talks, participates online. Thank you so much for participating. That makes the workshop what it is. And next up, I'm going to invite Kevin to come up and introduce today's plenary.
Good morning, everyone. I'm Kevin Reel. I'm the observatory scientist at Rubin Observatory. I'm part of the sitcom team. Our job has been for the last several years making this whole thing work. I cannot tell you how delighted I am to introduce the three speakers this morning. As we've gone through the last several years, things haven't always been smooth. And when things aren't smooth, the people you're about to hear from are the ones who smooth it out for us. This system would not be working without these three people. I'm really delighted to hear from them, hear their perspective on having made this whole thing work. And they have my gratitude forever for having made it work. So let's start with Brian.
I do need your help. I thought I knew how to fix that.
Yeah. I think we're good.
Thank you. All right, Friday morning. Thank you all for coming. And my name is Brian Stalder, and I'm very proud to say I'm one of the hundreds of people that contributed to this this project over 10, 20 years. And of course, I haven't been with the project for that long, but some people have. And I do have a daunting task to present on behalf of the construction operations teams, community members, and people that have just followed along on our adventure in making this project what it is, all the way from concept design and through to this final testing. So it's obviously a huge team effort. And, you know, this is probably just a small fraction of the people that have worked over the years on this project. So just want to acknowledge, you know, the gravity of what we accomplished. And, you know, given this section's theme is celebration. So now I get to sum everything up in less than 15 minutes. So here we go. All right, going back, design. So the original designers of the project had an ambitious scientific drivers that overarched to force the engineers to think outside the box. And they came up with a novel three-mirror design that enabled a very squat, fast telescope to be built that also could accommodate the largest astronomical imager ever constructed. So that was one thing. Then we have to build it in Chile. And so all the parts were shipped in the late 2010s and started assembly around the time of COVID, which was its own challenge, of course. And starting the integration soon after that, by 2022, we had the keys to the telescope and we started putting on all the subsystems that had already arrived on the summit in Chile. Of course, we didn't put on our most precious glass mirrors at that time. Instead, we had mass simulators to test the active components of those subsystems throughout that time. And of course, we heard last year the delivery of the LSST camera by chartered 747. And upon arrival in Santiago, not part of the plan, but we ended up with a police escort going down Ruta 5, and which was a nice kind of parade for several hours that day. And we safely delivered those 3 containers to the summit the next day. So that was really great to see as a kind of a send off to everything is now finally on site, and we can start doing the final integration. But first, we had 4 main test campaigns before we ever got on Sky. Actually, that's not entirely true. We did have these tiny telescope tubes that we used as star trackers to evaluate the dynamic performance of the system before we ever put glass mirrors on the telescope. So we tested for several years as we were building up higher performance and better understanding of how the system works. So here's a video of one of the tests that we did for slew and settle time. And we could test 3-degree slews back and forth between 2 stars. So this is a video again. And we did 30-second pauses between slews, as that's the design cadence. So it is a 4-second requirement for slewing 3 degrees and settling so that we can open the shutter at that time. So that was a great success in demonstrating that the telescope is capable of meeting those requirements. Okay, and then the end game came in early last year. We started the sequence of putting glass on the cells and installing them on the telescope, starting with M2, and then reinstalling ComCam, which had already been installed twice before that. So we got really good and good practice doing that. And then and finally installing the M1, M3 that was newly coded also last year. And taking advantage of a gap in the schedule while LSST Cam was undergoing final testing in the clean room, we put ComCam on Sky, basically not to verify its performance, but to verify all the other systems, in particular, things that had not been tested up till now, namely the AOS and science pipelines, which had only been tested with simulated or precursor data up until then. Okay, so what did it look like? Well, as you can expect, not everything worked right out the gate. Okay, so the first night that we were capable of getting on Sky with ComCam, the dome didn't open. So what do? Well, you could take images of the side of the dome, I guess. So this is a pinhole image of the side of the dome. This is the, at the center is the laser tracker in the middle of the M1, M3 mirror. And then you can see some of the deployable platforms that were extended that night just for easy access to the camera in case we wanted to do any final tweaks to the camera. So that was a painful night and disappointing. But the next night we did get the dome open. And the first thing that we wanted to do was to get twilight flats to get better image ISR accomplished. We were a little late getting on Sky, So those twilight flats, however, they didn't look as good as we had hoped. So first go at it, we're gonna chalk that up to a learning experience. But we got photons at that time. That was really exciting. I was really thrilled. But then we had to wait another couple minutes for the sky to get darker. And this was actually the first exposure at night with ComCam taken of the Helix Nebula. Shoot, the rotator isn't working right. There's a 50-50 chance, I think. So yeah, that took a couple minutes to fix. Thank you, Tiago. But we were still celebrating in the meantime. I don't think Tiago was celebrating at that time. So we fixed that. And then the first in focus properly tracking image, we got 2 arcsecond full with half max. And at that point, we handed over to AOS. And in the next several nights, we were getting sub arcsecond, sometimes even below 0.7 arcsecond delivered full with half max. So that was a great success and very exciting to see how rapidly we can get the system tuned up and ready for taking science data, which we did for the rest of that campaign, accumulating survey data, not wide field, but enough data to release to the public as DP1, which I hope everyone has already seen here at the meeting or when it was released not last month, but the month before last now. Okay, and immediately after ComCam comes off, we replace it with LSST cam, put it on the telescope, and then a month of waiting, pumping down, cooling, turning on CCDs, turning on back biases, having the back biases trip and doing it again and again and again. But finally we decide, okay, we're ready to go. Take the lens cap off. We haven't done that before on the telescope. So it's quite an involved process actually that involves removing some of the hand railing on the telescope using the huge bridge crane in the dome just to remove this tiny lens cap. But it's pretty critical. You gotta remove the lens cap if you want to observe the sky. So hopefully we don't have to do that too often. And do we have time for the video? Okay, good. All right. So let me switch over. We are on the day of the first photon. So this is a video that Alice and Rose put together. It's about 5 minutes. Buenos días. Buenos días, muchachos, ¿cómo están?
Hola, buenos días.
Buenos días, Oscar.
Bien, vamos a comenzar a revisar la actividad que tenemos para el día de hoy. Ya estamos inmediatamente entonces con Freddy. Freddy, buenos días.
Buenos días, estamos en posición de comenzar ahora inmediato el cambio de filtros. Y la tarea es larga, por eso me importa dejarla corriendo ahora para salir antes de almuerzo y poder inicializar el aceite al mediodía. Para esto tenemos 4 personas: Mario, Cristian Aguilar, Claudio Araya y Rodrigo Rojas en la grúa. También voy a estar yo y Travis. Por eso me importa dejarla corriendo ahora para iniciar un bloque de pruebas después de almuerzo. Balance.
Ya. Hay que escucharlo, ¿no?
Okay, we are switching this because of Gemini Lesser or the moon. I just want to understand the science behind.
Well, we need
For-
the U filter in for the first look campaign.
Okay.
Alex, tu m'entends? What a day, what a life.
But it's like a better view, you know? If you're looking that way, I can actually see what's going on over here.
Okay, thank you very much.
Parker.
Buen día.
Hola, buenos días.
Hoy necesito instalar un cable de power a la proyecta.
El proyector.
Ya, ok.
Que está desordenado arriba. Me dijo. El cable da lo mismo por fuera. ¿Está bien? Ya, bueno.
Llevemos los únicos entonces.
Lo fuimos. Goodbye.
I told the management that calibration will be ready for first photon,
Yeah.
and they didn't believe me, but if we can turn it on today, then I'm correct. Yeah.
La tarea principal para el día de hoy es con Anuar Zamora y con Doug Neal. Vamos a subir e inspeccionar todo lo que es el sistema de lubricación de motores, piñones, cremalleras y rodamientos.
Estamos verificando la posibilidad de reinstalar los fusibles una vez que Marcos de Face y Lorenzo puedan determinar qué pasó con la fuente. Así que vamos a reinstalar los fusibles y hacer posteriormente una prueba.
What you might have noticed is a tremendous frenzy of activity.
Entonces necesitamos dejar un dispositivo dentro, cerrar para poder desde afuera, sin abrir el gabinete, censar la corriente.
Queda cerrado el acceso al telescopio.
So, I mean, Freddy is doing balancing the telescope. It faulted, so now he has to recover it.
Acá venimos para el dump hanover para poderlo usar desde la sala de control. En este momento está bloqueado por otro sistema.
Wanna go?
Yeah.
Voy. Dale. Estamos listos para avisar para arriba, ¿no? Yo voy para arriba.
Moviendo 700. Y ya le había dado a mover el segundo a 700. Van a quedar los 290 de 700.
I don't know if it's okay. I just
I see a telescope.
I'm really happy that all of you made it to come here and that we can have this great moment together.
Ellos nos van a avisar cuando está el momento de prender fotón. Gracias.
You can ask more later.
There's only 2 voltages left.
Es emocionante que después de tantos años, 10 años, por fin vamos a ver la luz.
But we are taking an image and we are ignoring the dome. Now you go.
30 seconds.
30 seconds.
Don't touch.
Okay. All right.
It's gonna come. It's gonna come.
You have to watch the rest of it. Okay, so this is what came off the telescope, that first shot. We're less than 2 millimeters out of focus. Not too bad. Unfortunately, a fast telescope like that doesn't allow for that much room for error. So we calculated the size of those donuts and guessed 50-50 which direction to move the camera hexapod to get into focus. Second image, about 2 arc-second full width half max across the whole field. So that really makes you feel good that you can align those optics so closely with just a slight tweak to the focus. We were able to get decent field delivered image quality in that huge field of view. And throughout that night, we got better and better at it, achieving 1.5 arc-second that same night using the lookup tables from ComCam. So thank you, ComCam, for giving us a head start in this great commissioning period. Then the next night was even better, where we got extremely good natural seeing, which certainly helped us get even better image quality that week. And it's still getting better, but of course, there's a lot more work still to do. So it's just the beginning. Thank you.
While they're getting ready here, I was hoping everyone was gonna forget the rotator thing with ComCam. So thank you very much, Brian, for reminding everybody. We had so many discussions about what is the direction before we got there, and like, it's which direction the rotator assumes it's pointing, and I was sure it's pointing up. No, it's pointing down, and yeah, 50-50, and we got it wrong. Yeah. So while everyone is celebrating, I was like, now I have to fix this. Yeah, no, yeah, inside that. Yeah, so I'm gonna change a little bit, and this presentation is also about a group of people, a slightly different group of people that we usually don't talk about a lot, and it's the Telescope Inside software team, and all the effort we made to get the system ready for commissioning both ComCam and STCam. And one of the problems we had is that we're not only writing the software for each component individually, but we have to make sure that we get the system ready for the commissioning scientists to understand the system. We have to train the observance specialist, right? The people that will drive the telescope. And how can we do all that? But we don't have a telescope. We don't have the hardware ready. And sometimes when we get the hardware, what's the direction that it should move? So all that was a struggle that we have to go through. And I'm going to show a little bit how we did that. So to start with, our system, it's what we call a distributed system. If you go to the summit, you see one of the views that the OS use more often, which shows all the components that are running in the system, and they are either green, blue, or yellow or red sometimes. So each component there is controlling something on the system. And by splitting the system up like that, we allow the developers they don't need to know everything about the system. They can focus on their domain, and then we can write that piece of software independently and we just need to know how the other systems are going to interact with it. So that helps us a lot, but at the same time, it complicates how to orchestrate those components, how they are supposed to work together. And we took steps to make sure that we could test them, because we developed them individually, but we want to test them as a unified system. So here I'm gonna start with the two people that work really tirelessly on this part of the system. Russell and Dave, they both retired now, and they were instrumental to get the system, to help us design this distributed system and develop the framework that we use to develop each component individually. So they were instrumental for the development of the observatory control system. And they are both retired now, hope enjoying their life. So the next thing we did, we used the auxiliary telescope. And the idea that we had is, okay, what if we have two telescopes? If we design them to be as similar as possible, then we can use a lot of the much simpler system that it's the auxiliary telescope, and beforehand start developing all the tools we need to go on sky with Simony telescope. And this is a movie we made in June 2019 of the telescope, auxiliary telescope moving with the dome. The camera is in the dome, so the dome now is rotating, and the telescope is moving, right? So the show here that we can see, right? So when we move the telescope, the dome will synchronize with the telescope. And if you ever participated on a observing night, you know that that's what the Simony does as well. It's the same process. The same process that does this here for our telescope does that for the Simony telescope. So we developed one system and we had two or three, right? And at the time, Simony didn't have a cover on it. Patrick was instrumental at this part of the project. I think he was the calibration scientist. That was his title at the time. He was instrumental in first getting Oxtel there on time early so we could start doing this test, and then helping us develop all the tools to do the commissioning of the auxiliary telescope, and then later on design the calibration. For a time, we were operating Oxtel manually, and we decided, okay, when are we going to be ready to start using the scheduler with the auxiliary telescope? And I told him, oh, it's going to be August. I don't remember the year. It was August. And he said, oh, I doubt that's going to be the case. And I think like the last week of August, we were on Skype with the scheduler. And again, it's the same scheduler that we use for Simony. So when we start using the scheduler for Oxtel, we were testing the same scheduler that now we use for Simony, right? And that's, again, work we did for Oxtel, helping us out for Simony later. What's this? Okay, then COVID hit and we all went home, but we had a lot of work to do. So how can we keep working on the system and developing? Now we have to continue to develop Oxtel. We have to get ready for Simony. So one thing we did early on the project, when we were developing the system, is we decided that all the system, they must have simulators, right? So if a component is a pure software component, then it's fine. They don't need a simulator. But what about the mount? What about M2, hexapod, dome, rotator, M1, M3? So for all those components, we developed simulators. But the simulators, they are the same thing that run at the summit controlling the hardware. What we do is the component will talk to something that simulates what the hardware is doing. So the CSC, the thing that's actually controlling the hardware, doesn't know it's talking to a simulator. So what that allows us to do is have the entire system running in a simulation mode. And we have this, there's one here in Tucson that we are getting ready again. And there's one at the base in Chile. And we use this all the time to test all sorts of things. When we need to redeploy the system, when we have a new version of the system, we first test it on the test stands. When we have a new version of a component, let's say we have we found a bug on the hexapod at the summit, we try to reproduce it on the test stand, and then we fix it and we test it again. When we a couple of weeks ago or last week, we had an issue with slewing and waiting for the hexapods to be ready. We fixed that issue, tested on the test stand, and then we can go to the summit, and we have confident that that's going to work there. And if it doesn't, we can go back and see what was the problem. So in a sense, it's like you have the system running at the summit, and you have a kind of a video game version of it that you can play around to test things. And over, I've been talking about testing, right? So the team has inside our team, we have a smaller team. That's the build, test, and deployment team. So Rob is our test engineer. He's the one in charge of making sure that we can test every time we have a new version of the system, we can test it, and we do reproducible tests. We do repeatable tests. So we know, for instance, we had I think one of the OSs mentioned the daily checkout tests that we do at the summit. We do those at the test stands to make sure that the system works on the test stand. So we are confident that we can go at the summit and they should work the same way. And if they don't, we can homogenize them. Michael Ruther is kind of the head of the team. He's the one in charge of the deployment system. Our systems are deployed at the summit. Most of the components are on Kubernetes, so he's the one that manages that. And Amanda now joined the team recently. She's doing an amazing job with him she did a great job on when we moved to a more recent deployment, production ready. We had to scale out the components to make sure that if a component is using more resources than it should, we stop it, so we don't have a runaway situation. So she did an amazing job monitoring the system to see what's the resource the components use regularly, and then so we can establish the limits, and then we monitor them over time. And then another thing we had to do, at one point, the things was all in pieces at the level 3. And okay, we have the hardware here. The hardware is connected to power, it's connected to network. We can test it. So we should test it. So in addition to have the test stand, now we have the hardware here ready to go. And we took advantage of that as a training platform for the commission science and observance specialists at the time. We have M1, M3 here that was Peter Child. He's the main developer behind the M1, M3 system. He also does the thermal system, control system for M1, M3. And Taewei is the main person behind the M2 control system, the hexapods, and the rotator. He did an amazing job on those 3 components, rewriting a lot of the software we got from the vendors. A lot of the software was unmaintainable, so we had to rewrite a lot of the system. But again, this M2, for instance, is a control system that's interacting with glass. So there was a process of re-verifying all the control system once we rewrote it. And the same for the hexapods and rotator. They still have issues, of course, but they're mostly hardware issues, not software. So in the spirit of splitting the system up and testing, we also have the dome, the TMA. The TMA, when everything else was on level 3 split up, the TMA was up there at the dome ready to go. We could move the TMA, and then we could tell the systems that were sitting down level 3, hey, the TMA is moving, go do your thing, right? So for M1 and 3 and M2 was slightly more challenging because when the telescope is moving and M1 and 3 is mounted on it, the glass will experience gravity. But when M1 and 3 is sitting on level 3, it's not. So we have to make sure we could switch on and off the knobs to tell, hey, M113, don't care about gravity, just care about the lookup table. So it was a challenge like this that we had to face, but we designed the system in a way that we could do it, so we could test them. So, and one thing that you notice, so here we have the hexapod. I mentioned hexapods, but there's only one hexapod. The other one, I think at this time, it was being refurbished, which is the M2 hexapod. So we also took advantage of the simulators. So we could run one hexapod with hardware and the other one in simulation mode. And from time to time, oh, the telescope is not working. Well, let's use a telescope in simulation mode. Or M1 and 3 is misbehaving. Well, let's use a simulator. So we could flip on and off the simulation bit and use the simulator as summit to test things. And we do this from time to time when we have to test things as well. But now it's a lot less common. Well, Walter is the one in charge of the dome. I'm currently the one taking care of the telescope software, but this one was initially designed by Russell, the one that I mentioned at the beginning. And then we have the environment awareness system. This is the system, that's in the spotlight right now. It's the one that's supposed to be thermalizing M1 and 3 in the dome. It's a new system. We haven't we just recently started developing it because we didn't have anyone to take charge. So Brian Brundle joined the team and took charge of it. And Walter was the one that's mostly behind the ESS, which is the things that feed the EAS. So we have the weather, the DIM, and DREAM. They are on calibration hill. Those, well, the weather is the one that's ESS, and we put this all in awareness. So those are the two in charge of this system. And then there's the calibration system. We can't forget it. Remember Parker in the video mentioning that the system was going to be ready for first light. Eric Coughlin was tirelessly working with Parker and Elana to get a calibration system working. It's a system that's sitting on the dome, and we sometimes have issues, connectivity issues. So the system go up and down all the time. We're trying to figure out what the problem. Poor Eric, trying to figure out, oh, what can I do in software here to alleviate the problem. So he was the one that was helping out most of the time on calibration. And I think the last one, oh, there's two more. So of course, the systems alone won't help us drive the observatory. So we need to be able to visualize, and then the observing specialist and whoever is observing, they have to log what's going on. So visualization and logging, these are efforts done by Sebastian Aranda and Valerie. And this is the view I mentioned before that has all the components. So all the green components are ready to operate. The blue ones are in disabled, so they're connected to their system publishing telemetry, but they won't operate. And yellow mean they are in standby, so they're not doing anything, and they won't do anything. They're just sitting there waiting. And then of course, we cannot forget the one leading the team is Andy Clemens. He took the team when we were in a low, and he managed to bring us up. Brought the team together. He embraced the ideas that Russell and myself and Dave brought to get the system the state that it is today. So shout out to Andy. I can't assign him any component, but he's the one that lead us all. And yeah, this is how the software team got, integrate the software with the hardware and get the system ready for commissioning. And then we deliver it to the commissioning scientists to do their tests, and then use it to train the observing specialists. And that's how we got on Sky. And thank you very much.
Last year at this time, we got word that the calibration screen wasn't going to be ready for ComCam First Photon. And I thought to myself, installing a calibration screen. How hard can it be? And then I went down to the summit for commissioning in November and saw with my own eyes this enormous support structure that had already been maneuvered and lifted and installed into place to get ready for the screen, and realized that this wasn't any ordinary calibration screen. This was a Rubin-sized calibration screen, which is gorgeous, by the way. And we're good at improvising, no problem. We'll just take twilight flats. How hard can it be? And at least we have the collimated beam projector. The collimated beam projector is a device that aims light from the monochromatic laser into the telescope and measures throughput as a function of wavelength and position on the focal plane. It was designed in Tucson and was shipped to the summit in May. They open up the crate in May and find it completely busted. The baffle had fallen off and gotten crushed, and it just got completely destroyed on its way from Tucson to the summit. So they had to load it onto a truck with deflated tires and drive it back to La Serena, where it was basically rebuilt over the summer. And I'll come back to the CBP later. Then we went on Sky with ComCam First Photon, and at that point, it felt like we'd all been working on our components for years. We all knew exactly what we needed to do now. And at this point, what had changed is now we were all depending on each other in real time. Data management, which has usually imagined itself as having the luxury of being at the end of the chain, getting data from camera and then handling it afterwards, is now inside the AOS loop. The way the image processing that runs the AOS system and provides feedback to the observing specialists all runs on this engine of data management. The alert production and nightly validation pipelines, those run at the USDF, at the S3DF, at the SRCF, at SLAC. And the quick look pipeline runs on the rapid analysis framework at the summit. The quick look pipeline runs instrument signature removal on every image coming off the telescope, and then detects and measures all the sources and matches those to a reference catalog. We affectionately call that reference catalog Rykov's monster because it's this conglomeration of reference catalogs like Gaia, Pan-STARRS, Atlas, so that no matter where we look, there is a reference catalog to calibrate the data. And this matching is how we get quantities that everybody is waiting for after first photon. They want to know what is the actual measured throughput of the system. And in order to get matches, you need to know ahead of time where the general vicinity that the telescope is pointing. And on the 24th, the night we went on Sky, we didn't have this yet. But 5 days later, after days of furiously debugging on the whole stack of the system, we finally got 0 points. I remember the week after, I was at CCR 1 in La Serena, and I bumped into Keith. He asked, Yusra, do we have 0 points yet? And I said, what are you talking about? We've had 0 points forever. Yusra, we didn't, not 3 days ago. And I realized that the last 48 hours felt like an eternity. There was this extreme dilation effect going on. And I know all of you felt it too. That persisted all through ComCam on Sky. Everybody was up all night debugging. And for Merlin, that meant staying up until 10 a.m. UK time. Don't take his expression too seriously, because this really was an exciting, euphoric time for everyone. And Keith, I think Keith still hasn't slept since October. Keith, go to sleep. Okay, so those twilight flats, like Brian pointed out, was not easy. The sky brightness is changing quickly. The sky spectrum is changing quickly. Dome handover doesn't happen until 4:30, and that doesn't give much time to get the telescope ready in the window that you need. Stars are saturating. It was, thank you everybody for the twilight flats in ComCam on Sky period. For the CBP, it came back up to the summit, and Alana and Fritz started recommissioning the monochromatic laser in the lab. It took down one night of observing with ComCam because it was running on DDS, and there were too many systems running at the same time. Oops. 2 weeks. So then we got news that ComCam was going to be taken off December 12th, and that's 2 weeks away. Oh crap. So with 2 weeks to spare, ComCam's installed on the side of the dome, but still it was impossible for the components to talk to each other or to connect to the hardware and do the last pieces. It's now 5 days until we're taking off ComCam, and people are really freaking out. So there was this one heroic day where IT came up to the summit on a Saturday. There was a standoff with safety. Electrical had to authorize Alexis to lock the dome so that Fritz and Alana could go up in the man lift and connect to the hardware and perform laser surgery. They did manage to get 4 nights of CBP data before taking ComCam off Sky. And this was incredibly important because if they hadn't verified the magnification, we would not have been able to get a head start with LSST-CAM masks, and that would have delayed the use of the CBP with LSST-CAM when we went on Sky. This is the golden hedgehog that was placed for luck. Okay, so ComCam came off, and up north, the rest of data management, including science pipelines and campaign management, and the verification and validation team in system performance were hard at work commissioning the science pipelines and getting ready for data preview 1. There were phosphorescence and glow-in-the-dark CCDs, vampire pixels, edge bleeds, ITL dips, new detector effects that we had to build models for and mask. I described some of the other work in the science pipelines session back on Tuesday. Go check out those slides for everything else. This process was also part of the system verification that we did with ComCam, and a lot of it landed in Sitcom TN 149. And if we needed to get, okay, and then we went on Sky with LSST-CAM. Okay, so focusing with ComCam had exceeded everybody's expectations. If you looked at the DP1 data, the PSFs are pretty good. And so AOS with active optics with LSST-CAM, how hard can it be? I skipped a couple stories. How hard can it be? Well, turns out that if you're trying to focus a 3.5 degree diameter field of view that's 10 square degrees on an 8-meter class telescope, this is quite a hard challenge. And you heard about it yesterday in the image quality session. We're not just focusing any telescope, we are focusing a Rubin-sized telescope. They also mentioned that the thermal control is one of the poles for focusing, and that being able to open the louvers would be able to help this. And I thought to myself, opening some louvers, how hard could it be? And then the last trip to Chile, I saw the prototype actuators that were there designed to open the louvers and realized that these aren't just any louvers, these are LSST-sized, Rubin-sized louvers that need 2,500 pounds of force to be applied to each side equally with precision in order to prevent twisting. And you may have noticed a theme, which is anytime you find yourself thinking, how hard can it be? I've made data releases before. Ask yourself, have you done it Rubin-sized? I think over the course of commissioning, it has all hit us at different times, the sheer size of what we are accomplishing. I know I mentioned this on Tuesday, but even though I knew we've been spending this time building a machine that can cover a ridiculous amount of area ridiculously quickly, it still blew my mind waking up the day after first photon and seeing in my own QA tooling the area that we had covered that night without even trying. I have been enjoying asking people around this conference what their biggest surprise was during the commissioning period. And this was a theme that kept coming up again and again. So these are some of the things that people said. That we use petabytes in present tense sentences now. That the number of stars in each visit is more than any astrometric or photometric algorithm has ever seen. So this is the most stars per visit that FGCM or GBDES has seen. How big a number 189 is? Something that took 1 second to run for lattice now takes 3 minutes. And the calibration screen looks bigger than I remember every time I see it. Another, oh, and Colin reminded me of this one. During the ComCam on Sky period, we started out with 20 seconds per, per exposure. And then Tiago and team got that down to 3 seconds. And at around December 7th. And when that happened, the data started rolling in at an amazing rate. And we were now getting 100 visits per minute. And this was just an amazing thing to see happen. Another thing I heard frequently was just the quality of the data and how beautiful all the tidal structures were in the coads. What the M49 shells looked like. How many asteroids there were in that M49 field. Another theme was surprise that things just worked. For example, that AOS just works if we're pointing in a super dense field like the Milky Way. How fast ComCam was producing science quality data. That the ComCam data went straight through the DRP pipeline to coads, and the coads looked just like HSC. And then one didn't quite fit the categories, which was surprised that anyone who had signed up for the RSP would bother mining crypto just to make a couple lousy dollars. Don't do this, by the way, we will know. So I was at CCR2 last week, and one of the reviewers told me that on her telescope, commissioning was her favorite time and the time that she will always remember. And I can see how this is true. And I know this is just the beginning. We're still going to be learning about the observatory and the data and keep making things better over time. We are committed to that process and working with you over the years. But I hope that you realize that you have built something extraordinary already. That even though we're already in commissioning, despite all the close calls, all the late nights of furiously debugging, of getting data preview 1 out on time, of doing your processing constrained in the embargo rack, that even though there's still work to go, I hope you've had a moment, whether it was this week, 3 months ago, 1 month ago, that you realized we did a thing. And thank you. And thank you to everybody who shared surprises.
I think user meant that there was a discussion with safety. And while she told you showed you many things that were really hard, we never got stopped, right? This team, people all over the world, every problem that we faced, we've solved. And we're going to get on, we're going to continue on Sky. We're going to start the LSST, and we're going to deliver that fantastic data set. You saw from these 3 different talks, every area of Rubin in the community rolls a little bit different, but they all roll and they all achieve and they all keep going. And it's because we work together, everybody together. Everyone has a role, everyone contributes at whatever level is right for them, and we succeed together. But it's obvious that some folks contribute at levels that are outsized. And probably there's no one that has contributed over the decades at an outsized level like our project manager, Victor Cravendam, who's not been able to be with us today. He was online earlier. I hope he's still online, and I'd just like to invite him to say a few words if he would care to. I'm going to stop sharing. Victor, are you there?
I am here, Bob. Can you hear me?
Victor, I don't think any of us can thank you enough for all the things that you've done, all the sacrifices you've made, all the work you've put in over the years. And I just wanted to acknowledge that with this fabulous community. And I'd like, give you a chance to say a few words if you'd like to.
I very much appreciate that. I'm very sorry that I can't be there to celebrate this particular moment in time on this 2-decade journey, two decade plus. It was great to hear the last 3 talks, and I think those were representative of an incredible amount of work by so many different people, as has been mentioned. And my thanks go to everybody, because every little bit helped from every corner of the world in making this observatory everything that it is. And I look forward to seeing it shine. And I gotta say, there's nothing more satisfying than seeing and putting in this much effort to something and then seeing this many people use it and do really exciting things. So I very much appreciate everybody being there that week, being in Tucson this week, and look forward to decades of great science that comes out of this.
Thank you, Victor. Do we have any more? We don't have anything else. Thank you so much, everybody. Enjoy the rest of the day and safe travels, everybody.